No, what am I doing? Physics. Atoms. Einstein's equation. Open. How was the homework? Makes me worry. How was the homework? Oh, this really makes me worry. But you still.
Not sleeping in the night and sleeping all day.
You could have done the homework in GNIB, no?
No, I'm too tired. I'm sleeping in GNIB.
Alright.
And it's raining.
Yeah, of course. The rain makes physics more difficult. Okay. The first one is how much energy do you get from that? Okay. So on the left, let me add it up. Hydrogen and a hydrogen. So on the left, that's 2.01410 times 2. And then you have a helium and a neutron. So minus a helium minus neutron. So in question 1, you have this much mass. You made it. What happened? Yeah? What happened? Nothing happened. Alright, okay. This much mass is missing. So this is how much energy is made. You have it already? Good job. I shall double check for you. What did you say?
5.2235 times.
That's it.
What happens if you don't write the unit?
Then you lose 1 mark. That's what happens.
C is 3 multiplied.
It is. I think it's actually, yeah, it's actually 2.997 or something.
What?
Never mind. It's on your calculator. It's called C0. Ready? Okay, next one. Another one we need to balance. So on the left we have uranium-235 plus a neutron, and that becomes barium. Where's Ba? Oh, there it is. Krypton. And 3 neutrons. Is that everything? Yeah. Great. So in number 2A, there's this much mass missing. So then again, we can use our formula. The U is, what number? 17, and the C0 is 28.
Why is
Why is it this? Yeah? Yeah? So what I did was, I add these masses together, 235 plus this one, yeah? And then I add these masses together, and these 3, are smaller than these two.
Okay.
That's how much smaller.
I got a different.
Did you?
Maybe I minused it wrong.
Possibly. Okay, can I?
No. Yes.
Why number 1 is true and number 2 is true?
Because I made a mistake.
Ah.
Thank you, Andy. Right, speed part. How many nuclei are in 1 gram of, or how many moles are in 1 gram of uranium-235? So 1 gram of uranium-235. That means 1 mole makes is 235 grams. So then, therefore, 1 gram is equal to 1 over 235 moles, which equals 0.00426 moles. Then C is how many atoms there are. So the number of moles is 0.00426. So the number of atoms is the number of moles multiplied by Avogadro's number. What number is that on the calculator? 24. Oh, come back, Pam, don't go.
N is 1.00.
Which N?
No.
Huh?
No.
No what? Everything good? Great. Come back, Pam. Come on, wrong password. Uh-oh. Come on. You can do it. There we go. We're back. No. Too cheap. I don't like spending money. Right. This one, what happened? 2.56 times 10 to the 21 atoms, nuclei.
What if you don't write the word atom?
I think it's okay for this. Let me just get my pen back. Pen. Okay. D. Alright. So what's happening here, just to be very clear, this reaction, what do you need for this reaction? You need 1 nuclei of uranium and 1 neutron. So what's happening here is you have the uranium and a neutron is fired at it. Okay? So the question is, if you had 1 gram of uranium, how many of these can you get? It's the same number as the part C, because you need 1 atom of uranium-235, 1 isotope of uranium-235 for each reaction here. The neutron, you get that for free. It just gets fired out. So the answer for D is the same as the answer for C. Huh? Yeah, that's you need 1 uranium-235 per equation. So therefore the answer is the same. Okay? E. How much energy can you make from 1 gram? So you get this many reactions in 1 gram, and then how much energy is it? It's, where's it gone? This much energy. So I just multiply the two numbers. 1.607 multiply, or 10 minus 11. So the energy will be 1.607 multiply 10 to the minus 11 multiply 2.56 multiply 10 to the 21. .11 times 10 to the 10 joules. Is that okay? Yep. Is that okay? Yeah? So that's part E, yeah. Now, if a small city needs 10 megawatts of energy, how long could the 1 gram last? So, not a small city, more like a small town. Requires 10 megawatts of energy. How long could the 1 gram of uranium last in the power plant? So, power equals work over time. So time equals work over power, which is 4.11 times 10 to the 10 over power, which, what did I say, it was 10 megawatts, wasn't it? 4.114 seconds. I think I typed something in wrong. Let me check again. Yeah. Well, 1 hour, about. Um, 1 hour. 10 megawatts would be the power of maybe, I don't know, trying to think how much one home would use. 10 kilowatts. 10 homes. It could be, it could be maybe 100 small homes. 100 small homes maybe need 10 megawatts of power. So 1 gram of uranium would power them for 1 hour.
So the one tiny gram
Yep.
of uranium can do that.
Yeah. This is what I was trying to get across last time. There's actually a lot of energy released in this process.
So why don't you use uranium instead of like hydropower and windmill?
Well, it depends on the country, like in France, they almost entirely, like nearly 100% of the power is from things like uranium. But the problem with it is it's actually very expensive. It's very expensive. So it's not really worth the money. It's still cheaper to use oil and gas. Because with oil and gas it just comes out of the ground for free. Whereas with uranium, not only do you have to make it and be safe with it, then you have to clean it, put it away safely. It's a whole long process, which we'll look at later. So it's just too expensive. That's all. Okay, next one. What is the mass defect of copper 63? Okay. Now, copper 63 how many protons and neutrons does it have? Or how many nuclei should it have?
63.
It should have about 63. In fact, oh, I don't have my periodic table. Can we get out how many protons and how many neutrons? Protons and neutrons. Yeah, just a quick type in there to the Google machine.
Oh, 29.
Thank you. 29 protons. Yeah, so that makes 34 neutrons. So the mass should be 29 protons. Can you check your notes, Irene or Andy? What did I say the mass of a proton was using the U units? 29 something U's plus something. Well, you know what? It's okay. No, it's okay. Because I'll just use my calculator, because the calculator has protons and neutrons on it. So let me see. 29 protons plus 34 neutrons. So the mass should be 29 mass proton, 34 mass neutron, 1.0545 times 10 to the minus 25 kilograms.
But you told me yesterday you can't use like this. You can't use like mass of total mass of electrons. You have to use that because like yesterday I got a different answer.
I think what you were doing was you were using your calculator, which gives it to you as kilograms, but in your formula you had the U in it still, or something like this. I can't remember. You were mixing up using the U and the kilograms, so you choose one or the other for the question. You don't mix them.
This one's kilograms.
This is kilograms, yeah. Okay, now the mass of copper 63 is actually 62.91367. Let me add in more decimal places here. 1.054535529 times 10 to the minus 25 kilograms. But actually, when you look at it, it's really 62.91367.
That is using by A.
Yeah. Which is equal to 1.04470539 times 10 to the minus 25. So there's some mass missing called the mass defect. Yep.
U is on
Yes.
Oh.
1.05453526 minus 1.04470539 0.009830135 times 10 to the minus 3 kilograms. That's the mass defect. In fact, if you wanted to, you could cancel that with the kilo to just get grams. But you don't have to do that. Right, so what is the binding energy? So the energy, B part, the binding energy. So if I multiply Oh, sorry. So sorry. I forgot about my 10 minus 25 here. So this is actually 28. I never typed this into my calculator. Right. So you get 8.8349 times 10 to the minus 14 joules. And the last part, what is it per nucleon? So then, per nucleon, you have to divide by 63. So when we divide by 63, we get this. This. Yeah. Oh yes, the unit, of course. Joules per nucleon, but we'll just write joules. Okay. Okay. I think that's it. Good. Right. Okay.